So now we can move to the next talk by Professor Houssem Kasbaoui. So it's my pleasure to introduce Professor Houssem, who is an assistant professor in the School of Engineering of Matter, Transport and Energy at Arizona State University. Houssem's research interest lies in massively parallel simulations of multiphase and aerosol-laden flows for environmental and aerospace applications. Hi, Houssem. Looking forward to your talk.
Hi. Do you see my slides?
Yes.
Okay, awesome. So it's great to be here today. It's a real honor to be speaking in this workshop. Of course, we're celebrating Professor Bala, and just like Professor Prosperity mentioned, is a very impressive researcher who had many significant contributions. So I remember from 2 years ago, Bala was at Arizona State University for a seminar, and he gave this very impressive talk on particle resolved DNS and extreme scale computing. But I think what impressed me the most that day is that I learned that he walks over 20,000 steps a day, which is very impressive for me because I struggle to be, as fit as him. So, Professor Bala, it's good to have you, a member of our community. Thank you for your contributions. Thank you for championing junior faculty, and happy birthday.
Thank you.
All right, so I'll get going with my presentation. So today I'm talking about how you can manipulate turbulence using inertial particles. Okay, so this is a motivation slide, but every one of you is familiar very well with the field, so I don't really need to introduce this too much. All I want to say is that in Arizona here, we're very aware of this problem here. This is called haboob, these dust storms that hit the valley very frequently, cause all sorts of problems. So people do experience turbulent particle-laden flows fairly regularly, even though they are not experts in the field. One more implication that I thought interesting, and maybe you're not aware of, is what this YouTuber came up with. Yes, okay. It's a fluidized bed hot tub. It's very hilarious. If you have time, go check it out. But basically, they fluidized the sand here, and he shows in that video that basically you can float in this sort of fluidized bed here. As you can see from the tennis balls, they float. But if you cut the air, then you instantly freeze in that sense. So it looked fun. I want to try it one day. Okay, so Balachandar and Eaton wrote this seminal annual review where they have this figure here on flow classification. So particle-laden flows really span different regimes and require different numerical approaches. What I want to focus on today is the so-called semi-dilute dusty flows. So this happens when you typically have solid particles or liquid droplets in a gas. The particles can have a wide range of sizes going from typically micron particles, right? 10 micron to 200, maybe 500 micron. The volume fractions in these semi-dilute dusty flows stays relatively low. So we'll say it's between 10 to the -5 to 10 to the -3. These are high density ratio particles. So we can refer to them as heavy inertial particles. Now, this figure here is very interesting because we have the volume fraction and we also have the particle inertia on this axis. But what I want to say is that there is also another dimension to the parameter space, which is the particle mass fraction, also called mass loading. So for the semi-dilute dusty flows, the volume fractions are very low, but the mass fractions are comparable, which makes them very interesting and makes them especially challenging and resist modeling. And part of the reasons why they're incredibly difficult to model is because they display extreme multi-scale behaviors. I'll show today that the particles can span 6 orders of magnitude when they cluster. And also because what we know about the underlying suspending turbulent flow may be different in these flows. The particles do change turbulence, and that leads to behaviors that are not well understood. All right, so what does it mean to be in the semi-dilute dusty flow regime? Well, looking at the volume fractions, So just like I said, typical volume fractions are 10 to the -5 to 10 to the -3. It means that the suspension is fairly dilute, and that means that particle-particle interaction is negligible. So we don't have to really worry about things like collisions in these flows. However, the particles do interact through forces mediated by the fluid. So that's what I will talk about primarily today. Inertia is significant, which means that the particles deviate from the fluid streamlines, and when they do so, they exert a drag force on the fluid. So there is a feedback force from the particles onto the fluid. Whether that feedback is significant or negligible really depends on the mass loading. And in these semi-dilute dusty flows, the mass loading is going to be order 1. And that means that the feedback force from the particles on the fluid is significant. And this is usually referred to as two-way coupling. So these are two-way coupled particle-laden flows. All right, so these flows lead to significant flow modulation. Okay, so let's see an example of flow modulation. So what I'm taking here is a canonical flow. This is homogeneously sheared turbulence. This is a flow that's been studied extensively. So we do understand a lot about this flow. We're starting with homogeneous isotropic turbulence. And what we do next is shear this turbulence box. So there are two numbers that characterize this flow. It's the Taylor microscale Reynolds number right here. And we also have a shear number, which determines how strong is the shear. So let me show you an example of what happens in a single phase homogeneously sheared turbulence. So these are simulations at starting Reynolds number of 21. Over the course of the simulation, this grows to about 200. The shear number is 27, which shows that this is a very strongly sheared turbulence, which does fall within the realm of rapid distortion theory and so on. Okay, so this is a cut in the vorticity magnitude field, showing you what happens at t equals 0. So you're starting with an isotropic field. And as time progresses, and this is the non-dimensional shear time, you see the elongation of these structures, the turbulence becomes anisotropic. And also you see more of the light colors, less of the blue here, which means that the turbulence has been increased thanks to the energy added by the base homogeneous shear. And in fact, you can measure the turbulent kinetic energy. You see that it grows, and you can measure the dissipation, and you also see that it grows. So all of this is fairly well understood and also compares really well with rapid distortion theory, which is an analytical theory. Now, what happens when you add particles? Okay, quick note on the simulation method. So we're using this Euler-Lagrange approach developed by Capicilato and Desjardins in their 2013 JCP. It's based on volume filtering, and we basically track individual particles and solve the fluid equations with volume fraction terms and also the feedback force from the particles. Okay, so I'm showing you here what happens at the non-dimensional time 5. Okay, so this is our simulation box. Please know that I have gravity here, so gravity is being applied. So the particles are sedimenting in this vertical direction. Now, if you don't have any particles, so this is the vorticity magnitude field that you get. If you have these particles, which are 50 micron water droplets in air, this is a large simulation, by the way. We got over 1 billion particles here. The Stokes number is 0.06. The mass loading is 0.5, so significant. I mean, visually looking at the vorticity magnitude field, you see that it's been enhanced. You have more of these red regions. So visually speaking, the turbulence has been augmented. And if you look at the volume fraction field, you see that we have these sort of void regions here. We have these small clusters, so the particles distribute inhomogeneously. Now, with the second case, where we have 90 micron water droplets, so slightly larger water droplets, what we observe the opposite behavior. Basically, the turbulence has been diminished. Right, so this is a turbulence attenuation case, and then the particles also, cluster along these very, very elongated clusters. Now, these are particles that are 90 micron, but this cluster that I'm highlighting here has a length of 1 meter. So this tells you that this is a highly multi-scale problem. really difficult to model, and so on. But the fact that we can enhance or attenuate turbulence using particles that we just tune their size, sort of tells you that it is actually possible to manipulate turbulence using inertial particles. These plots here show you the turbulent kinetic energy and the dissipation rate, just emphasizing the fact that with these lower Stokes number particles, we have an augmentation of turbulence, and with these higher Stokes number particles, we have reduction of turbulence or turbulence attenuation. Okay, so here are the following questions. Now, aside from anecdotic observation of turbulence attenuation or turbulence augmentation, is there a way of actually understanding what's happening? And I know that Professor Shankar Subramanian is doing a lot of work on modeling here. But perhaps we can understand this flow modulation by just looking at these vortices and their interaction with particles. Okay, maybe that can tell us something about whether the particles are going to enhance or attenuate turbulence. And if you understand that, is there a way of actually controlling flows, right? So perhaps in applications where we have these resilient flow structures like here, trailing wingtip vortices, perhaps spraying some water droplets can disrupt these flow structures very quickly and make it a little safer for airplanes to land. Perhaps in applications where you want to damp vortex-induced vibration, you can add some particles and see a damping of those vibrations. And in long-distance pipeline for natural gas or oil, maybe adding the appropriately sized particles can lead to skin friction drag. So I'll talk about how particles interfere with vortex dynamics, and I'll also talk about this problem here of skin friction drag reduction, and I'll actually show that it's possible to do that with spherical inertial particles. All right, so we do know a lot of things actually about particle-vortex interaction, and we have this picture that's usually referred to as preferential concentrations. So this is from a paper by Squires and Eaton. I think they were the first to coin the term preferential concentration, but people have been talking about this effect earlier than that. And basically the way it goes is that your particles are inertial. So when they're in a vortex region like this, they tend to be expelled outwards. And as a result, they tend to accumulate in straining regions. So particles preferentially sample straining regions over vortical regions. Now, this is great, and it's a very useful approach, especially in one-way coupled flows. But what it doesn't tell us is how this particle motion here, or migration, results in a modulation of the carrier flow. So that's what I'm interested in answering. And this is perhaps going to tell us how turbulence is dissipated or reduced by particles. Okay, so to test that idea, we're looking at particle-laden Lamb-Oseen vortex. So this is research done by my student Shuai. So what we have here is a Lamb-Oseen vortex, and it's a representation of an isolated vortex tube. This vortex is incredibly resilient. So there is a lot of work out there, theoretical and experimental, numerical, that shows that this vortex is just resilient to anything that you throw at, especially all kinds of 2D and 3D perturbations. And that's sort of what explains why those trailing wingtip vortices remain coherent for very long times. For this vortex, we can define a Reynolds number, which is a ratio of the viscous time scale and the inertial time scale. So the inertial time scale is just the time that it takes for a fluid particle to make a full circle at the location where the velocity peaks. So as I was saying, this vortex is very stable. So these are some of our simulations showing normalized velocity magnitude and normalized axial vorticity. And what you see is that not much happens. Actually, what's going on is it is slight viscous diffusion, but it happens at an extremely slow rate. Then we add particles, and we can define the circulation-based Stokes number. We're varying the Stokes number between 0.1 and 0.4. And the mass loading, we're keeping it fixed at 1. Okay, so let's see what happens with the particles. Okay, so this is sort of a picture that we sort of know from preferential concentration. So what happens is that the particles are gradually ejected from the vortex core. These particles accumulate along these annular clusters, so ring-shaped clusters. And with increasing Stokes number, this clustering happens faster and the formation of the void bubble happens faster. So this is something that may be predicted just by thinking about the preferential concentration mechanism. Now we know that preferential concentration is the key aspect for this clustering here. So maybe we can write that into equations and figure out a clustering time scale that makes the behavior self-similar. And to do that, all you have to do is just look at the particle mass conservation equation. So this is an equation for the number density here. The term on the right here is the preferential concentration term. It relates to the divergence of the particle velocity field, which is compressible. And you can immediately see that there is a difference between strain, the strength of the straining region minus the strength of the rotation. So doing just a scaling analysis, you can figure out a clustering time scale, tau c, which is the inertial time, tau f divided by Stokes number. In other words, the Stokes number is the ratio of inertial time scale and clustering time scale. Now, when you plot everything with respect to tau c, you see that we have sort of the same dynamics happening regardless of the Stokes number. And we can also measure the radius of this ring cluster. And we can find that it scales with square root of t over tau c. The coefficients here, the 0.4 and 1.4, are practically insensitive to Stokes number. And the takeaway is that the cluster forms in about 3 clustering times. And later on, it's the growth of the ring slows down because it scales as square root of t. Okay. Now, what actually happens to the flow? So this is the part that we don't really know. Well, here what I'm showing is the axial vorticity, and you can see that vorticity, the particles have a significant effect on vorticity. We can see that there are these sharp gradients, that the vorticity distribution sort of increases in size. And sure enough, if you look at the radial profiles, you see that the vorticity distribution just flattens quickly, much quicker than you would have with just viscous dissipation. And we have these strong vorticity gradients and so on. So overall, the vorticity is damped in the core within just a few clustering timescales. Okay, so what does it mean for the kinetic energy of the fluid? Well, the kinetic energy of the fluid also drops significantly within this short time frame. One thing that's interesting is that the smaller particles, the 0.1 particles, lead to a larger drop of kinetic energy, but keep in mind that their clustering time scale is actually larger than the clustering time scale for smaller Stokes number particles. Okay, and how can we describe this behavior? Well, we can describe it by looking at the energy balance. So now what we see interesting happening here is that we have a particle production term. So we see that there are basically 2 pathways for flow modulation. The first pathway is through particle production, and the second pathway is through the modulation of entropy. And if we look at these 2 terms, what we see is that the particle production here spikes early on and then decays within 3 or 4 tau c. So this is the first order effect, but the dissipation or the entropy here also increases, which is not what you would have in a 2D particle-free vortex, because in a 2D particle-free vortex, you would only have a decay of entropy. But here it grows, and the reason why it grows is because, again, you can write an equation for entropy and see that there is a particle production term here. And that's really what contributes to this growth here, which is an interesting behavior. All right, so we understand that particles can basically enhance the dissipation of vortices as they're ejected out of the vortical cores. So how can we use this in applications with to do flow modifications of engineering relevance? And the first thing that comes to mind is to just take a turbulent channel flow and dump particles in it. and see if we can actually reduce skin friction drag, because that has economic relevance. So that's exactly what we're doing. And this is research of my student Himanshu Dave. So we have these simulations of turbulent channel flows with particles. The Reynolds number is 180. The Stokes number is varied between 6 and 90, and the mass loading is held constant at 0.6. Okay, so let's just go to the main result, which is the change of skin friction drag. Now, this is very interesting. There are results in the literature out there that tell you that particles are going to increase skin friction drag, particles are going to decrease skin friction drag, or not have any effect. Well, what we're showing here is that it really depends on Stokes number. So for the Stokes number 6, we have drag increase. And for the Stokes number 30, 60, and 90, we have drag reduction. And here in this table, I have the percent drag reduction. So it's about 10% for Stokes 30 at this mass loading. And we're actually doing additional simulations at mass loading of 1. And we're seeing a drag reduction of 18% for Stokes 30. Okay, so this is significant, right? And what's also interesting is that the drag reduction, we do get drag reduction for Stokes 30, but then it diminishes with increasing Stokes numbers. So this does seem to be a sweet spot where we get, the highest drag reduction, and we don't know yet what that sweet spot is. But
Houssem, sorry to interrupt. Can I request you to wrap the talk in a few minutes?
Sure. Yeah, we'll do that. Thank you. Okay, so when we think about drag reduction in these turbulent channel flows, we usually think about near-wall coherent structures and what happens to them. So we looked at the near-wall coherent structures, the drag increasing and drag reducing cases. And in both cases, the near-wall coherent structures are damped significantly compared to the unladen turbulent channel flow. So the reduction of the near-wall coherent structure is not the full story. There is more to it. And in fact, if you look at the stress, so the balance of stresses in such semi-dilute dusty particle-laden channel flow, well, what you see is that you got your viscous stress term, you got your Reynolds stress, and you also got a particle stress term. Okay, so this is actually quite similar to what happens with polymers, because you would also have a polymer stress term. So these are the plots for the drag reducing and drag increasing cases. Well, what we see here in red is the particle stress. Okay, so that's why looking at turbulent stresses is not sufficient. You also have to consider these particle stresses. What we see is that the drag increasing case of Stokes 6 actually does lead to a more significant reduction of the turbulent shear stress than the drag reducing case at Stokes 30. But what we see is that the viscous stress here widens in the Stokes 30 case, and that's because the particle and turbulent stresses are shifted to the right in the drag reducing case. And sure enough, that's the reason why you get an increase in mass flow rate. So maybe I forgot to mention that these are simulations at constant pressure gradient. So drag reduction manifests as an increase in mass flow rate. So you can write this expression here, and you see that this integrand that you get here, which is negative, diminishes when these curves basically move to the right. Okay, so those are our observations, but really, what is so special about this case Stokes 30 that we don't have for the case Stokes 6 of the drag increasing case? So when we looked closer, we found that the particles have these very peculiar clusters forming near the walls that we call particle ropes. So these clusters essentially span the entire domain. And that's why we're doing these large domains, the simulations, these larger domains, just because we get these ropes that are so incredibly long. The bigger the domain, the longer the ropes. Here we have ropes that are over 5,000 wall units in length. Now, what I want you to also keep in mind is that these ropes, they're not collisional clusters. The volume fraction here is about 10 to the negative 3. And these ropes, when you look at the velocity, streamwise velocity, you see that they're aligned with the low speed streaks. And what's also so interesting here is that the spacing between the low speed streaks, which is usually 100 wall units in unladen turbulent channel flows, regardless of the Reynolds number, now increases to 180 wall units. So the particles do mess up with the near wall coherent structures. And part of the reason why these particle ropes appear is because they interact with these near wall coherent structures. So when you have counter-rotating vortices like this with an upflow, you have an accumulation essentially of the particle that may extend upwards. But in other regions where you have a downflow, like here, the particles are pushed to the wall where they cluster more. Whether these ropes are stable or not depends really on the particle inertia. So we're finding that with Stokes 30, these ropes are stable, but with Stokes 6, they're not. They're basically destroyed by the turbulence because the particles are less inertial than the Stokes 30. So drag reduction does look dependent on whether we get these particle ropes or not. And there does seem to be a critical Reynolds number, critical Stokes number for which we do get drag reduction. All right, so I'll leave you the conclusion slide. I want to acknowledge my collaborator, Professor Anubhav Roy, and my students, Shuai, Himanshu, and the funding. And with that, I'll take any questions you may have.
Thank you, Houssem, for the interesting talk. So we can have a quick question. Okay, so in case there's no question right now, please.
No, Alfredo had a question.
Yeah, sure.
You are muted, Alfredo.
It should not be. Yes. Now you should hear me.
Yes.
Okay.
Yes. Sorry. So with your method, can you control the accumulation of the particles? So are you sure that you can reach a situation in which you have realistic accumulation, so particles do not overlap with each other?
Yeah, so in this case, we actually do have collisions turned on. So the particles are not overlapping because they would collide. But even though collisions are turned on, as I was saying, the volume fraction is really low in those particle ropes. So
Thanks.
odds of collision still remain very low. We are studying this, what controls the spacing between these ropes. We want to understand really what's the role of Stokes number and what's the role of mass loading to figure out whether there's an optimal Stokes and mass loading combo that gives the highest drag reduction.
Briefly, gravity was not included, right?
Yes. So in this case, we didn't ignore gravity. Things would change, but the idea is we want to figure out the effect of inertial forces. So that would be perhaps applicable to much higher Reynolds number flows.
Thank you.
Yeah, thank you for the question.